Hello everyone, welcome to the fifth talk on our series of on our lecture series on the representations of topological groups. So today's talk will be given by Aprameya Girish Hebbar and it will be on Haar measures.
Thank you. So today we will talk about Haar measures. So the first thing is why measure subsets of a group. The answer is clear. We want to carry out integration. We want to sort of mimic the techniques of calculus and on a possibly nice enough group. So we can't do derivatives. I mean, derivatives would require a lot more structure, but we can always do integrals, and integrals always start with measures. Okay, so the example that we are motivated from is R plus with the Lebesgue measure, which we denote by M or even dx. So since so what are nice enough groups on which we are going to carry out the integrations, we will always take our group G to be locally compact and Hausdorff. So why locally compact Hausdorff? So first of all, let's settle with the definition. Locally compact means on like for every point x in G there exists U open containing x such that U bar is compact. The closure of U is compact. This is the definition we are taking, just in case we have some issues with the different definitions. So why we need like locally compact? So that is because Unison lemma guarantees that the CCG, which is the space of all continuous functions with compact support, this is not a null set. This is guaranteed by the Unison lemma. For instance, you take any 2 points, take like even for 1 point, I mean, you take 2 compact sets, then you can have a function that's 0 outside and 1 in the first compact set, and so you have like a function that's supported in this particular compact set. So that proof is like.
Could you explain what the support exactly means?
Okay, so let's see. So first, CCG is a set of all continuous functions with compact support. So by sup f, I mean all those x in G for f from G to C. Yeah, again, these are all continuous functions in the sense functions f from G to C, complex numbers. So the support of f is actually all those f where x is not 0. Or you can take its closure. So this has to be compact for f to be in CCG. And Unison lemma guarantees that this is not actually compact. So that's one thing. And second thing, locally compact groups are the best approximations of whatever happens in Rn. I mean, Rn is also a locally compact group. It's not compact. But like in most, like even in like measure theories, we want to mimic everything that we do on Rn on locally compact spaces. So that's the first thing. And then let's settle some notations. So throughout the talk, we will be writing CG for set of continuous functions f from G to C, and CCG is this, and CC plus G. This is all those f in CCG, which is non-negative, like which takes f of h is non-negative for all h in G, and f is not identically 0. We just have to take non-negative value, and it's not identically 0. Alright, so just to be clear with a few, we'll just recall some definitions. So the first one would be what is sigma algebra. Sigma algebra is a collection of like let x be a topology or x be any set, like x be any set. So sigma algebra is a subset of power set of X such that it's closed under countable unions and complements. So this is a routine definition of sigma algebra, and measure mu is these are all the measurable sets. Basically, if you can measure A and B, you can measure their unions and complements. So on a sigma algebra, B, a measure is any function that takes V to 0, infinity included, and such that empty set belongs to, that's also axiom. So empty set has to be 0 in the sense it can't be infinity everywhere. And as our intuition suggests, whenever you have a disjoint countable collection of disjoint sets, this has to hold.
Is that complementation relative complementation between each other or with respect to?
If A belongs to B, then X minus A belongs to B. So this should hold on. So this is what is a measure, right? And this one of the best examples is the measure on R that we put. All right. So with that, we are not interested in any measure in the sense it should not be very bad. What we want is let's say even for R, we expect something like 0, 1 compact set to have a measure nice enough finite measure, not it is not having finite measure first of all, or something like we need some very nice regularity properties, and those measures are what are called as random measures. So people start whenever you have a topological space X, then let's say X be a topological space. Now we consider the Borel sigma algebra. Whenever I say Borel sigma algebra, it just means the sigma algebra generated by open sets. In a sense, you take open sets, you take their unions, complements. I can replace this by closed sets as well because closed sets, unions, complements, all of this we consider Borel. So our measurable sets are basically the open sets, closed sets, their unions, and their complements. Yeah, and it's not Now with this, so if X is a topological space with Borel sigma algebra on it, then we say a measure mu is random if firstly it should be finite on the compact sets. It should be finite. At least our intuition says that these are some nice enough. Second thing is what's called as outer regularity. Outer regularity says that for any u, you can write u, the measure mu of u as mu of mu is u for mu. Mu of e should be equal to infimum of mu of u, e inside u. Basically, given any e, you can approximate it by all the open sets, and we have the following equality. This is for every e Borel, in particular for open. And third, it's inner regular in a sense. For any open set U, it's actually the supremum of compact sets. Stay inside here. This is for all U open. In the sense, given a compact set, let's say on R, you can given an open set, you can actually approximate it from inside by compact sets. Alright, so this is what we know as radar measures, and we are going to study only these measures on the topological space because they are nice enough. I mean, you can use all these properties.
In the second point, is it U is compact, right?
No, U is a open, U open, and A compact.
So for
this regularity condition, is there any motivation why we say?
Yeah, because all of these hold for level measure on Rn.
Okay.
So, and these properties are extremely useful for.
Is this an attempt to abstract those?
Exactly. So for any topological space, we want to like we want to sort of mimic whatever is happening on Rn, and again this is for locally compact also.
So will the, like in a sense, a converse of that, will that hold? So here we have open sets can be approximated from the inside by compact sets.
Exactly.
So can compact sets be approximated from the inside by open sets?
Compact sets are closed sets, so you can have it.
Exactly.
Or by outside,
And what about compact sets being regulated from the outside by open sets?
That's here, but
No, I'm talking about
from inside, I think you can, like, they are closed sets. So there are, like, on Rn it does hold. There's no problem with that. For others, maybe one of these can imply that. Alright, so all of these matter because our Haar measure that we are going to decide, that we are going to define, is actually, we'll take it to be a radar measure. Next thing is one of the it's a central theme in whenever we do measure theory, that's Lee's representation theorem. In the sense, it basically says that there is a, for example, let's say you have a measure, right? Then you have a functional. Whenever I say functional, it's just a linear function from the set to the complex number. You have a functional on CCG. That is, you take f, integrate it. This is you get this from free if you use a measure. But what Lee's representation theorem says is that if so again X is a locally compact Hausdorff space and you are considering Borel sigma. So let's suppose lambda is a linear function. Right. So what I want to say is that lambda is actually an integral for a lambda is actually an integral. That's what I want to say. Okay. But then if this is the case, our measure only takes values in 0 to infinity. So whenever f is greater than if f is positive, this integral is also positive. But my lambda has to be positive for it. Okay. So such that lambda f is greater than or equal to 0. This is a complex number, but I am imposing the condition that it's a non-negative real number. Whenever f is greater than 0, then if this is the case with lambda, then you have a unique Borel measure mu such that this happens.
Is this Borel measure dependent
On lambda, because essentially what is happening, if you take any let's say function, then it's basically giving you the integral. So this measure actually governs whatever happens, whatever happens with the same function. And so it's a Borel measure. It's also a radar measure. And further, it's actually a complete measure. That's what's carried by Haar. But we don't mean that. So whenever you have a positive linear function, such linear functions are called positive linear. And this has nothing to do with continuity or anything. It's just a linear map from CCG to C, such that it's positive. Then you directly have that this is actually it actually comes from a measure. So we have a one-one correspondence between positive linear functions on CCG and the radar measures on G, X on G.
this topology on G? Does it induce any natural topology on CCG?
Oh yeah. So basically here we don't need that, but CG it induces the natural topology with the norm. For any function you can just use the suit norm.
So then
CCG will be a subspace of CG.
and will that be?
It won't be complete.
I see. Then, but CCG is also has a vector space structure.
Exactly. CCG has a vector space structure. But for this theorem, we don't need any topology. But you can actually consider C naught of G, the set of all functions which vanish at infinity. Again, that is a different definition. And CCG would be a dense subspace of C naught G. And you can have a representation theorem for that. But for the purpose of this talk, we will be using this particular. So what I'd like to bring to your attention is that existence of a measure implies existence of a linear functional, very trivially. Existence of a linear functional by this representation theorem, if it's positive, it implies the existence of a measure, and that's unique as well. Okay. So now let's come to the main topic. Haar measure. So let G be a locally compact Hausdorff space. I'll be writing LCH. So with we end up with Borel. Okay, fine. So then mu Borel radon measure. A radon measure on G is called Haar measure if now comes the important thing. This will be a left Haar measure. I'll define what's a right Haar measure. It's called a left Haar measure. So what's the only this is a you can give a radon measure can be given on any topological space. But what's the group structure? That's a multiplication. If this measure mu respects the left multiplication, then we call it as a left Haar measure. Alright? So this should happen for all x in G, for all E in the Borel measure. Borel measure of the Borel measure that we are considering for this particular Borel sigma algebra. So for instance, like y, the thing is, let's say you consider a measure. You are giving this interval 0, 1 as the measure 1. But then if that measure takes for the interval 1 to, if it's taking 2, that's totally contrary to it, right? We want it to, if we are considering half plus, we want it to be translation invariant. That's how we started with volumes, right? We should have the same volume. Similarly, if you rotate a solid in R3, it should be invariant rotations and translations. So that is sort of captured for the local locally compact Hausdorff like this.
Is subgroup or subset?
E is any subset. Yeah, E is any measurable set. So E is not any subset. E is any measurable set. So the open generated by all the open sets. The sigma algebra is generated by all the open sets. So you can consider it to be any open and closed for the that it's just unions and combinations. So with that, mu is a right Haar measure. If mu of Ey is mu of E for all y and so let's see some very basic let's make some basic observation on the new definition that we have made. So suppose mu is a left Haar measure. Right? Suppose mu is a left Haar measure. Now if you consider this mu tilde and defining it to be mu of E inverse. This is for our E in the Borel sigma. Right? So if I set this, then mu tilde is a right Haar measure. set of polynomials. And similarly, we have E dot F. That's the representation that we will be using. So then Ey is actually equal to Ye, which is mu of E inverse, and that is equal to So this actually says that it doesn't matter if we study right half measures or left half measures, because we can always go from one to the other just by this association. So we'll be studying studying only left half measures, and we can carry out all the conclusions for the left half measures. All right, so that's one thing. The second thing that you can observe is if G is compact. If G is compact, what happens? By the radon, since any Haar measure is a radon measure, it should have mu of G less than infinity. So I can scale the measure in order to make mu of G equal to 1. If mu is a measure, then if I multiply it by any positive constant, then it's a measure. And all of these things hold true because just by multiplying the positive constant. So I can multiply 1 by mu of G if I have any other measure to make this, right? And we call such, if this happens, we call it as a normalized left half measure. And we
going to assume that mu of E is equal to
no, this is a new method. This is a new method that I created. It's for going from left to right. That's all. Yeah. So okay. So we'll be interested in when G is compact, we'll always be interested in such normalized left.
So I have a question. So in case the measure is both right and left, obviously if the measure of every set was equal to that of the inverse, then it would be both right and left.
Yeah.
But does the converse also hold that if the measure is both right and left, then mu of E should be equal to mu of E?
No. And it's just invariant under left transition, so it's not invariant under right inversion. Yeah. So motivated by these representations here, we also would like to see how left half measures connect with the linear function, right? So a few definitions. By Ly, so let f be a function from C to G to C. Then by L by f, that's another function that takes x to f of y inverse.
F should be just from G to C, right? F should be from G to C.
Sorry. F is any function from G to C, then okay. So yeah, we'll say Ly of f is a new function which is translated to y inverse, and our y of f will be f of xy. And we have the phi inverse just for the sake that we would like to have, which you can easily. These Ly, these are on HSCC, on functions on. So L by Lz will take a function f to some other function, which will be same as that obtained by L by Z. Alright. So now we'll connecting our measures with linear functions. So let mu be a left half measure. Okay, we just start with radon. So we have obtained a radon measure. Okay. So then we have mu is left Haar measure if and only if so basically you have an integral here, integral f dv. Now you translate the function and then again take an integral. If they both are equal for every translation, then it's actually a left hand. So here we are having a statement about measures, and here it's a statement about basically linear functions, right? So this allows us to find measures in linear functions as we'll see. So one way is actually very easy. That is, if you assume this, if you go this way, like for the proof. If you assume this, then I just can. So for which function? Yeah, this should be for all x. For all, I would say for all measurable x. Yeah, so integral f is there, right? So you first take this left translation, then you take its integral, and you just take its integral. Then they both should be same. Yeah.
So how would we define that?
No, mu is already a radon measure. Suppose you start with a radon measure, then it's a Haar measure if and only if the integral is invalid under left translation.
So can we put a Haar measure on any locally compact modular?
Yeah, that's what will be we'll come to that it exists.
On any locally compact version this with the okay. So all that we require is our GVLC.
Yeah. And in fact, we'll show it's actually unique. Yes, but like for
So just like as a rudimentary method, if I take R star, which is basically constant,
exactly.
it is obviously LCM. But a measure on this will basically mean your translation invariance basically is actually multiplication.
Exactly.
So no matter how large my open set is, it will still have the same measure. So is there an actual realizable measure for this R star?
So we'll complete this and we'll get to the example. Okay. So just what I'm trying to say is that it's invariant under the left translation. No. So okay. For one way we will say f is equal to the indicator function. Then you get mu of e here. Here you get indicate like this indicator function is just what? On e it's 1. So Ly of e will just be equal to so it will just be equal to it will take it to what? It will take it to y inverse of it. So this will be indicator of y inverse of it. So the left hand side will come out to be not y inverse of it, I think y. Yeah, y. And the right hand side will be this. So that would imply the integral of indicator function is just a measure of that side because it's 1. And similarly here we have for the other directions, which is slightly non-trivial, we'll use a powerful tool for these representations here. What we do, it's not clear how this invariance and the left translation will give you a measure. So what we do is we consider the following linear function that takes f and will give you L by f dv. Right? So this is a positive linear function because if f is greater than 0, then L by f is greater than 0. So this integral is greater than 0. And by this representation theorem, we are guaranteed. Oh, sorry. I think I reversed this direction. Oh no. Oh yeah. Oh, fine. So by this representation theorem, we are guaranteed that there exists some Lorentz measure mu such that this holds, because it's a linear function, and this linear function should also come from a particular measure, right? Now we can take f is equal to, now we can this actually like will show that mu has to be again one can take f is equal to and finish off the proof. So you get mu of e, you get mu of y e, and since but it was left half, so you get mu of e equal to mu of e for all e, so mu is equal to mu, so you can just replace it by getting this particular. Okay. So now let's go to some concrete examples. So first example would be G finite. Okay. G finite, it's already compact. Okay. So our measure will actually be equal to the counting measure. How modest. So to just count it. This is invariant under left translation because the cardinality is still the same after left translation. And indeed, the integral would actually become a summation. So here, in the sense, if you, okay, so we'll talk about linear functions that I should cover. Okay, so this is the Haar measure. The next one, B is equal to R plus. The Haar measure is the Lebesgue measure. That is here. And so similar to R. Now coming to the example that we pointed out. This is your proof. So what I will claim is this particular measure. So one of the left Haar measures is this for S4. So to get a mu of a comma b, what will be the measure for this interval? Just integrate from a to b, and that's equal to ln b by a. So even if you scale this, the factors will cancel out, and you still get the same. It would take a little bit more work to actually show that this is indeed left invariant, you have to use some.
But this will, of course, it was not necessary, but it will lose its standard invariance, which is
Exactly. Okay. So yeah, one would need more, but you should be convinced that this actually does the work. Because if you start with, let's say, AS, then you have a AS and you just do a like substitution S bar, you can have something like T mu is equal to S by A. No, u equal to T by A. So that will give you back.
And to extend this to the general multiplicative real group, we'll just, since it has two disconnected components, the measure is just added.
Yeah, you can do that, but I'm not sure if you can add that. So yeah. So you can just take mod t instead of I also. If you have two, the only thing that's giving a problem was this can be negative.
Yes.
So we have taken care of that by introducing, and we can go to C star as well. One Haar measure, that's one Haar measure. So again, observe that this is also a right Haar. This is also a right Haar.
These are not commutative.
Exactly. That's right.
And that thing goes with
Yeah, for E inverse, so E inverse here would be 1 by A, 1 by B. So you have 1 by A, 1 by B, no, that's the whole. You have A by B. And that you have.
Yes, in fact, the negative.
Exactly, yeah.
So
So
there is a conflict.
So for C star, what would you guess? One left parameter would just be equal to dx dy, considering it as R2. Just take x squared plus y squared. In fact, we'll generalize whatever is happening here on manifolds and R very shortly. And finally, one of the most important groups, the circle group. So what you can do on circle group, you can give what is known as an arc length measure. So we already have parameterization, right? 0 to 2 pi. You can parameterize this circle via the function f that takes t to e to the power it. We have a measure on this. You can easily put a measure on this, right? M of f inverse of this. This is a continuous function. Taken as f inverse is the open set here, or open set here will be pulled back to open sets here. So this will be measured to be like for the first thing, and you can take the Labelle measure of that. So yeah, in all this, one should actually notice that this is compact. So I can actually divide by mod 3 to make the measure of the whole group to be equal to 1. Similarly, I can actually scale this by the measure of the whole circle, right? To make this one. And what is, if you take S is equal to G, f inverse of S is equal to the whole of 0 to 2 pi. And so it has a measure 2 pi. But now we scale it so it has measure 1. The whole circle has measure. Yeah, so I actually want to discuss these examples with their parallel linear functionals. So let me introduce a bit of linear function and we'll come to these examples once again. So with this here in light, one can actually introduce some important linear functionals. So what? Yeah. So again, G topological group, and F psi is a linear functional on CCG. Okay, so for the moment, let me just set for the set of for defining it, it's either defined on CCG or defined on CBG or defined on CG. CBG is just the set of bounded continuous functions. So again, in CCG, continuous functions generally look like this. But in CBG, you are allowed to go to infinity as long as it is bounded. So CBG will always denote a set of all bounded continuous functions on G. Right? Okay, so let's suppose psi is a linear function defined on any of these domains. So we make the following definitions. The first one is psi is left invariant. Psi is left invariant if the intuitive definition is that you take a function, you left translate it by Ly, the function Ly, and then you take its value. This is actually equal to the original. For all, I will just write domain here. Similarly, this was for like, again, similarly you can do right with value just by taking R by here. I'm not writing that down. And psi is positive. If you saw earlier, if psi of f is non-negative for f in CC plus f. Again, psi of 0, the entire function 0 is actually 0 because it's a linear function. So, and the 0 element here is just a 0 function. Okay, and now comes the important thing that we will be interested in. Psi is, suppose if psi is both invariant, in the sense left, right, both invariant, left, right invariant, and positive, then we call it as, then we say psi is invariant mean. Why it's called as a mean will be apparent very soon. And then, so first of all, okay, so this is one thing, invariant mean. And now we introduce I think you cannot see if I write a line here. So if G is compact, this definition is only for compact topological groups. If G is compact, then psi is said to be Haar mean if psi is invariant mean. First of all, psi is a mean, and such that psi of G is equal to 1. So it's basically so let's to unpack all the definitions. Haar mean on a compact group is a positive left invariant, right invariant linear function. And normalized. Sorry. Oh yeah. Xi of that integral. Right. Yeah. How can I have been using the measures, so psi of phi is equal to 1. Okay. So basically, so what are we saying? It should be positive, left invariant, right invariant, and normalized. Okay. So to be, I mean, the first thing you will notice is left Haar measure exists if and only a left invariant positive linear functional exists. Given a Haar measure, just consider this functional f going to integral. That's the left invariant because of this theorem, positive. Okay. But on the other hand, given a left invariant positive linear functional, first thing it's a positive linear function. So raised representation theorem will guarantee a measure when it comes from a measure. And since it's left invariant, this equation is satisfied. So one has to use the left hand. See, you have that the measure from which the linear function came is the left hand. Alright, similarly for right and left and right Haar measure exists if and only an invariant mean exists. Right? And on a compact group, left Haar and right Haar measure, left and right Haar measure exists if and only a Haar mean exists. So that's what makes the existence of Haar mean and Haar measure parallel. The statements are very parallel. So let's now, since we know that measures and linear functions are parallel. So what's the linear function associated with this? So that's basically you take a function f and average it out. Right? So forget about this measure for now. So this is a left invariant, this is positive, this is average right invariant. So this is actually a invariant mean. And this is what is known as the average. So that's why we are calling our definitions involve the word mean. Next, for these, for Rn plus your function, your LF will just be dm, the derivative. Now for this again, since you have a measure, just integrate. So once we are done, derived the measures, just integrate f, and then with respect to this particular measure. Yeah, but here it's special. So you can actually give without even knowing this, you can give a nice linear function. positive linear function. This is also a mean because I mean it's left invariant. You rotate the function and then integrate it, it will still be the same. And what you should note that it arises because of this measure. I mean, you can just take the integral, then this function f will come out. So that's why you have this integral right. So since we have seen the since we have seen enough examples, I think what we do is we'll maybe do another example before. I think it's good. So we'll see what are amenable groups. So amenable groups were defined by von Neumann when he was working on the Banach-Tarski paradox. So he defined amenable groups as G is amenable. So G is amenable. There is no A. G is amenable if phi from CB to C positive. Alright, you can directly get as invariant. And invariant mean exists. Obviously, we want it to be non-zero. I mean, if you take every function to 0, that's also a functional, but invariant, but we want it to be non-zero. So this condition is like it's a more stronger condition implied because you generally have linear functions on CCG, but this wants us to put linear functions on CBG. But if G is compact, then we have CG equal to CPG equal to CCG. So the existence of this particular I defined here. CPG is just the set of all bounded continuous functions. So CCG consists for R, CCG consists of functions like this, like bound functions. But CPG can consist of it need not vanish at anything. I mean, it can even just but it has to be bounded. So it's a bigger set than CCG because So if G is compact, all of these match. When G is compact, all these match, and the existence of this invariant mean will just be parallel to the existence of the Haar measure on a compact. So it turns out that this definition is actually very important, and a lot of work, there's a lot of literature on amenable groups. Alright, so let's do one more example before going to the main thing that Haar measures actually exist, and surprisingly they are actually unique. So the example I want to do is this. Let G be a group embedded in Rn. So basically, it's in a sense the underlying manifold of G is embedded in Rn. So one example you can take to be G as an R. G as an R. For this, n is equal to n squared. So it's embedded in Rn squared. You can take un, you can take so and so on. So we'll cover all the cases like at once. Now we would like to construct a Haar measure for this particular group G. Now we already have a Haar measure. I should say left Haar measure, but I'm speaking the words left. So we already have a Haar measure on Rn, and that is the Lebesgue measure, right? The dx. Take any functional, you integrate with that, or take any set, you can just integrate the indicator of that particular set to get the result. So our guess. So what are our guess? So the most simple measure we can construct using this is f naught of x. basically our guess is measures mu of v is just we integrate this particular fixed function f naught on the set. That's what we will be doing here. See, we have that we have what dt is a level measure on r, right, and r0 is a manifold that's inside r. So we r f naught that we derived here is 1 by 2. So we integrated yeah, so we took this particular measure. So that's what our guess is. This is our guess. So we want to come up with a nice f naught. So what are techniques that we have? So we have the change of variables formula. Right. So if you have a open set U or a measurable set, so any measurable set, and phi is taking u to phi u an injective function, and if f is almost everywhere differential in the sense in the regular sense, so that f of y minus f of x is equal to a matrix times y minus x plus order of the norm of y minus x. Then we have this you integrate, so you can integrate f on u, and that will be same as, so yeah, let's just try this to be. So you can integrate f on v, and that is same as, yeah, f is measured. So integrating f on v is same as integrating f on u. Oh yeah, I will make sure I write the variables. Oh, nice. That's what I did. Not it. Yeah, exactly. You are doing it. So yeah, okay. I just want my f0 to be measurable. That's all. So this is something. Yeah, this is something that, like, in general, in multivariate calculus, it's true for the C1 function set. But C1 functions for continuous function set. But you can actually do it for measurable functions as well. Although you may need some more technical assumptions. I won't cover this part. Alright, so according to our guess, what is the measure of a set? That is basically we integrate f naught of x dx, right, on this particular set.
What is f naught here?
F naught is some function that I don't know, but I am guessing that this function, if I take this function and multiply it by with my measure, direct measure, then it will satisfy. Correct? So I hope you understand studying that. Yeah. So what do I need? I need mu of as to be equal to mu of s. This is something I need. Right? So let's try to use this. So we have s. Now this is left multiplication by a. So I'll still write it as LA. Although this LA there was different because it was acting on functions. Here it's acting on elements of G. So it's sending it to AS, and then F is some function sending it to F naught. So then according to this formula, F naught of V on S is same as on AS. Sorry,
yeah.
This is V. So it's same as F naught of your phi is LA. So LA of U with LA dash of U d. So this is actually equal to mu of S, and I want this particular. So mu of S I want to do this. So what is, okay, let's just keep it the rest. Yeah, so at this point I'll make one assumption. So what is LA? It just left multiplies by a particular element of G. But we are in Rn, so left multiplication is actually a linear map, although we are not defining it everywhere. So suppose that I have in G that LA of x is some multiplication by a matrix plus some addition, possibly addition. It may not be just a multiplication, although it's a translation. In that sense, it's yes, it is an active matrix. So this is some matrix Rn cross M. It is some matrix, right? So if this matrix multiplication holds, then what do we have? What is LA dash? The matrix associated with or some write as P LA dash, P LA of P. So that will be equal to, so yeah, that will just be equal to this AA.
If LA is linear, BA must be 0, right?
Yeah. I mean, you take so on R you take left translation. It's taking
Acha.
0 to
Okay.
some vector it's translating. So this need not be a linear map, but we are assuming that this the multiplication goes like this. Although you can guarantee that for all matrix group this will happen. So then your derivative is this. So what do we have? So that's just determinant of A. Right? So I want to make take f of f naught such that this happens.
Just hang on a minute. Yeah. You remember 2 or 3 lectures back, there was that discussion on measure preserving maps, measure preserving isometries, and why they must be affine. You see that function LAX is an affine function, and essentially speaking,
Yeah,
the
yes.
talking about some kind of measure preserving transformation. That's the reason why there is a PA.
Right.
Oh yeah. Oh, so
Same logic.
this is an affine function, yeah.
Yeah.
But I think you can always have that for all these matrix cubes that we have. Alright, so we have this. So now to finish it off, I just need to make sure this comes out to be f naught of u. Correct? If this is f naught of u, then this equation is satisfied. So I'll choose my f naught of u to be 1 by determinant of AU. If I choose this, then what is f naught of LAU? LAU is just AU, okay? So that is equal to, so let's just verify this particular equation holds. So f naught of AU is 1 by determinant of AU. But by our definition, you can actually verify that the matrix multiplication by 2 elements is same as first and then second. But then determinant is actually multiplicative. So this is actually 1 by with AU, AA and with AU. And this particular term cancels out with this. So this one cancels out and you have 1 by determinant of AU, that's again F naught. So this is satisfied. So the main, so what we have derived is if G is embedded in Rn and dx is the dimension of Rn. This is on Rn. And if the multiplication Ax is actually the same as multiplying a matrix AX, again x as a vector in Rn plus BA, a vector in Rn, a matrix in Rn cross n.
I think that should be A inverse X. Because LA acts like A inverse X, right?
No.
You multiply it by again B, then it is what? A B times this whole thing plus BB.
Right.
Then you have A B A O. Then you might, and if it's not working, I think you just need to do, but I think it works. Although I'm doing the calculation that A of AU equal to AU. So if this holds, then one Haar measure is mu of S equal to dx. Sorry, I think I should just write one Haar measure as dx by determinant of Ax for S. is one Haar measure. So we'll apply it to the group that we have got, GL and C. So GL and R, since we are talking about R, and one can actually do this for C as well. Alright, so for GL and R, so what is the multiplication? You take, so let's suppose let's fix x, fix S. So how does it act on a matrix set? What is Sx? So choose a basis. So this is inside Rn square, right? So you choose a basis. If you choose a particular basis, and these are two matrices in GL and R. But if you write x as a matrix, then this particular multiplication is actually just nothing but block multiplication by S. So what you do is you take the first column here, second column here, and so on. Now you calculate Sx. Then you will get that this is actually the same as what like. So this is in again and this equality, there is a bijection involved in equality. This thing is inside Rn square. This thing is inside Rn square. This thing is inside GL and R. So there is a bijection. So this is a linear algebra fact, but it's actually diagonal with S. So what is the determinant of AS, or the multiplying matrix, or whatever we can call it? So that will be determinant of S to the power n. Right? So that is just this is the Haar measure for GL and R. Although you should observe here that if you multiply by right, then also you get the same. So in fact, for GL and R is actually also this is the first example of a non-abelian group for which you have left and right Haar measure to be a single Haar measure. So and then once like all of these are also all of these are special cases of this theorem, right? So here what was your multiplication? It was multiplication by some t. So you have put that here. N is equal to 1. And then here, yeah, again. So that justifies this as well. This is nothing but mod z. So when you multiply by z, so all right. Yeah. Okay. So now let's come to the. So since we have seen a lot of examples, we know Haar measures exist for all of these examples. But does it exist on an abstract level? So if I start with a group G, can I say that Haar measure actually exists? So the main theorem is, again, let G be a topological group. Okay. G be a locally compact group. Then left Haar measure exists. Haar measure mu exists. If mu is any other Haar measure, then there exists some k non-negative real number. Just like mu equal to k. Yeah, that should guess that. It's not even 0. Just take out the 0 case. The 0 measure is also good. Okay, so again, mu equal to k means mu of e is just equal to k times mu 1, and that's also a Haar measure. Okay, so the first thing is that, okay, so a bit of history. This was first demonstrated for some special groups. Maybe, yeah, in second countable group. So second countable groups, it was demonstrated by Haar himself. And 191 actually proved its uniqueness part. This is the existence part, this is the uniqueness part. 191 was the first one to prove its uniqueness part. And Wayne was the first person to provide a proof on all locally compact groups. And that the accountability assumptions in Haar's proof was actually unnecessary. Yeah. So before going one corollary that you can see right from here is that if G be compact, if G is compact, then harmony exists. Oh yeah, so harmony exists is not clear from here. All that is clear is positive left invariant linear function is exists. Only this is clear. But we will show that this actually implies harmony exists. So that's something we come to the summary. Alright, so for this theorem, I'll give a sketch of a proof. And although the proof is very intuitive in the sense, I mean, at least how we begin is intuitive. So let's suppose G was R. How would you construct a? So first thing, we don't want to construct a measure. We want to construct a left invariant linear function. Okay. So what is a left invariant linear function on R? That's the integral. So coming to the integral, so how was the integral defined? So the first one more note before that, before even going to that. So what's the goal? The goal is to construct phi left invariant positive, right, linear function. So we'll restrict to the positive functions first, and then we can try to generalize it, right? So for first we want to restrict to the positive functions. How do you define an integral on CC plus G? So for example, this is the graph of a function of R. So on CC plus G, how do you define an integral? You would go like this. Right. So that's because, so here what are you using? We are using the fact that indicator of 0, 1 exists. And that's exactly what you are sort of shrinking from 0 to a, translating, and then taking a particular length. So that means this particular simple function actually bounds this CC plus function CC plus d, and you are taking the infimum, right? But here we don't have this phi 0, 1. What we have is another compactly supported continuous function, positive continuous function. So we use what we do is instead of this, we'll take another function, okay, and then we'll translate that, we'll shrink that, and then use. So we'll use another function, and hopefully it is additive. Hopefully it is additive, or hopefully the property that we need. Obviously it will be positive, no problem. So hopefully it's additive. So what our fixed function that will be denoted by phi. And again, the way the function that we want to apply this on is f. Okay. All right. So our first guess. So what is, let's say this is, I mean, how do you write as f function? You would write it as Cj, indicator of some interval, right? Indicator of interval. So here my indicator function is replaced by the in essence integral of phi. So I would like to define this particular quantity phi or f as infimum. Okay, infimum. What do I want to do? I want to bound f by a function that depends on xj by j equal to 1 to n x1 to xn you basically took phi, you translated it, you you took I'm going to see it. So you made it big enough so that this whole function you also add up. So you are adding different translations. I mean there can be two bounds, like two bounds. In that you need one translation here or many and some here. So you are adding them up. You are majorizing, like you are bounding f with this, and then you are taking only this part sigma cj. Why? Because so our the step integral of a step function here corresponds to sigma cj integral phi. Because by translating phi, you are not changing its integral. By multiplying it with cj, you are changing its integral by cj. So what you are doing is essentially this all these integrals. Hopefully, I might have done it a bit bad. So all these integrals they count this much, and I am just dropping this phi because phi is somehow in fixed function. I'll take care of this particular integral phi in the next step. Alright. So that was with the intuition. So my I phi f would just be equal to phi f or because this is f phi. So it's just f phi, and I divide by f naught phi. I'll fix a particular function f naught. So then so intuitively this is some cj integral phi. This is some, let's say, dj integral phi, and this guys cancel. So you essentially this will end up with a fixed number, no problem. So you essentially have this. So this is what I want to be my integral. Okay, this is what I want to be my integral. So what are some simple properties you can observe from this? So the first thing is f1 plus f2 is just f1 and f2. Right, because if you just take f1 and f2, I mean although sorry, not exactly, I should say.
It's less than.
Yeah. So you start with two sigma Cij and sigma Dij for f1 and for f2. Then if you add them up, that will clearly majorize f1 plus f2 because f1 will be less than or equal to sigma Cj and f2 will be less than or equal to sigma Dj and some Yj. These xj's can be different, but we'll have some elements in G. So that this equation will hold. Okay, so the other side is what's we want to see if it happens or not. So this is okay. What about homogeneity? It's homogeneous, no problem. Because if you replace Cf for some again for C greater than C, then you have a C here, but you can introduce a C here to make things equal, and then you get a C out. So that's not a problem. The next thing is it's actually translation invariant. Because no matter how you translate, we have allowed for translations in our definition itself. So you can observe, although it might need some require some work, but you can observe that it's actually translation, at least intuitively on how we have defined. That's okay, and it also satisfies this. So I am writing all this for this bracket, but you can write all of this for I phi as well. I phi f1 plus f2 is less than I phi f1 plus I phi f2. Alright, and next thing. So,
Wait, what is the last line? F1 and F2 are defined in this context.
yeah, f1 and f2 are cc plus g. Such that f1 is less than right. So it will be measured. So if you have two functions one below the other, then yeah, it's actually this one is actually obvious. Alright, so now coming to some harder observation. This is less than f psi phi. Psi is again another function in the future. Now that is because if f is less than or equal to summation a term that's operating in an infimum here, and phi is less than or equal to sigma dj L by j phi, then f, I mean you can just put this inequality here to get sigma cj dj L xj yj phi. And with this, you have this, I mean, take infimums, you have this equality. Although I'm not doing it exactly, like I'm not doing it rigorous, but you can see that if you can match, like this is like f, I mean, yeah, this is some property that we need. And one thing that you can immediately recognize from here is that f phi is actually, so I'm taking some f naught such that this quantity is positive. I mean, I need it to be non-zero. So you can observe that this is actually f phi. So with respect, if I take my psi to be f naught, then this is actually equal to f naught f. So if I go here, f naught f phi, so that's just f naught phi. Means f phi. F naught phi. Okay. And this is less than or equal to again another. I just take phi f naught. Okay. So what this basically gives is that my I phi of f will lie in this particular interval. Always. Just dividing by f naught phi, I get what? 1 by f naught f and f naught. This is one observation. Just alright. So now let's come. If it's like, is it additive? Is this I phi additive? That's the main question. So in other it's not. And why it's not? Maybe that we're not choosing some nice enough indicator function. So, but luckily what we have, like this is not very far from being additive, because so if you have epsilon greater than 0, right, then there exists open V containing EG containing the identity element such that I phi of f1 plus I phi of f2 is less than I phi of f1 plus f2 plus epsilon for all phi such that support of phi is inside it. So it's additive up to epsilon, or approximately additive, as long as, or I should say, I mean epsilon near to additive if you are choosing certain phi inside a neighborhood of EG. That neighborhood is guaranteed to exist, and this is something I'm not doing here. So we work using this. So the thing is, I mean, it's not very hard to know this as well. So we are guaranteed additivity as long as I mean we are in this particular order, and any phi, as long as we choose this phi in this prescribed open neighborhood of EG, we have epsilon additivity. Yeah. So with this, now our search for linear. So in all this, what's the thing? The thing is, like, it need not arise from a measure. That's the thing. Our linear function need not arise from a measure. We cannot find a measure and then say the measure, like the linear function came from the measure, because finding a measure is hard. So what we do is we say that a particular linear function exists and it's additive, although we know nothing about it, like the measure it comes from. So we use some, although I call it topological tricks. So basically you consider this. So let's define this to be x. Depends only on f naught is fixed. Okay. So take this particular product. Now what is this product? So I am varying f over cc plus g. So times 2 CC plus or psi from CC plus to 0 infinity with psi of f inside xf. I mean, any element corresponds to a function like this. Need not be linear, but it corresponds to a function like this, such that psi of f is in xf. Correct? And in particular, we have I phi f belonging to x for all functions. That's what we proved here. This bound has nothing to do with phi. Good. So now, how do we pinpoint the linear function that we want? Consider this particular set. It's almost I phi. It's sup phi inside it. Okay. So this is a set of you collect all the phi such that its supremum is inside you. So that like in that case, you can use this, right? But notice that this is actually a compact set because it's a closed set in a compact set. It's compact. So, but further, it also this KB, we a neighborhood of E. This has finite intersection property. And why is that so? Because I mean, if you collect all the functions which support inside for any finite fraction Vj in any, if you collect all the functions that are inside, whose support is inside all of these, then trivially it will belong to this. So any function here has support inside all of every Vj. So therefore, the intersection is finite intersection is never ending, and that shows there exists, although we have no guarantee about its uniqueness, there exists I because of the finite intersection. A theorem from topology guarantees that this happens, since these are all compact sets. And this is the I. This is R. So to finish off the proof, observe that if you have epsilon greater than 0, right? If you have epsilon greater than 0 and given some function, although it will be clear why I am taking this, and a neighborhood, we are starting with all of this given, right? If you consider this particular open set f in CC plus D, where UF is equal to XF except for all these FJs, where I choose this to be I of Fj minus epsilon, I of Fj plus epsilon. So I belongs to K, its intersection. So I is actually inside S. So I am consider this particular open set, and in the product topology this is actually open because only finite, this is actually a basis input because only finite many are not expressed. So it's open in X and I is inside U. So this U has to have non-empty intersection with each of these KVs. So in particular, I is inside U and each of these Fj's also belongs to, I should say, not I is inside U. Okay, yeah. So U is open and contains I, not a problem. So that's okay. So, and what this actually means is that U has to have some non-empty intersection with KB. So there exists some phi such that this happens. For all j equal to 1. In this sense, this I actually comes close to I, one of the I phis. So what do you do in order to show that I is actually additive? You consider f1, f2 and f1 plus f2. So the first equation we have is if1 less than I phi f1, if2 less than I phi f2, if1 plus f2 less than I phi f1 plus f2. And we are guaranteed that these all are epsilon here. If I take b smaller, small m1. So that means that all of these are epsilon here for every epsilon. So you have an either. Similarly, you can do the you can do this left invariant because of the left invariance of alpha. So that will show that your I is actually I exists, and that completes the proof of the existence. So since we are running out of time, I think I will just give a reference to the proof of the uniqueness. So it's unique up to scalar multiplication, and one reference is like the Polland's book on a course in abstract harmonic analysis. I'm running out of time. Good. So what's more important than the proof is its corollaries. So what can we derive from this? So I promise that I'll show that Haar mean exists. So, okay, so this says that a left Haar measure exists. But we have a lot of questions. Is this right Haar measure? Under what conditions is this right Haar measure? Okay, so what are we guaranteed? We are guaranteed a left Haar measure exists, a right Haar measure exists, right? But what happens is, if G is compact, a left invariant mean is right invariant. And I should say positive. Okay. So let's suppose you have a left invariant mean, and I'll write just CG because CG is CG and then a CG. So this is the left invariant mean. What do I mean by that? First of all, it means M of LYS is same as M of L. Okay. So in order to show its right invariant, let's consider MG. So I define MG, another linear function, defined by it takes any function f and gives out M of RG. You write translate f and you write translate f and then take its M and take M, right? So but then look at that. This is actually MG's left invariant. Why? Because if you put L by F, LYF will come here. But Ly and RG come here because Ly is multiplying by left, RG is multiplying by right. So Ly can come out. And M of Ly RGF is just M of RGF. So you can get back MG of F. Correct? M is left invariant. So according to the uniqueness, MG is K times M for some M. Correct? So what does alright, so what does that mean? That just means that that just means that M of, so Mg of F, what is Mg of F? It is just Rg of F. So M of Rgf is just K times M of F. But if I assume that the chi g, if I assume more that it's actually M chi g equal to 1, if I assume this, then K will also come out to be 1. Why? Because it is put F equal to chi g, so this is again chi g, and this is chi g, so we get 1, K equal to 1. So if I have normalized left invariant Haar mean, then it's actually right invariant. So therefore, Haar mean exists. Because we demonstrated for a group, compact group, we demonstrated a Haar measure exists. When the Haar measure exists, you have a positive left invariant linear function. With left invariant, we have shown that it's actually right invariant. And this doesn't happen always. I mean, it actually doesn't happen always. And so that is a definition. If left Haar measure is right, is also right Haar measure. I can say if the left Haar measure actually, but because since we have shown its uniqueness, if the left Haar measure is also right Haar measure, then we say G is unimodular. So a group is called as a unimodular group if it has a measure, that's both left Haar measure and right Haar measure. And we have seen obviously abelian groups are unimodular. Right? But we also see compact groups are unimodular. And GLNR is a unimodular group that's neither abelian nor compact. But no, take note that not all subgroups of GLNR have are unimodular. I mean, I can give you a particular example since one example that I had in mind was this particular. It's actually the affine transformations on R. Yeah, affine transformations on R. This particular group is a subgroup. It's embedded in R. But you can check that it has the left Haar measure is 1 by y square dx dy, while the right Haar measure is 1 by x dx dy. So 1 by y. This is omega. Sorry, mu L. This is mu R. This is one example. So it doesn't get every subgroup. Again, why is this happening? Because the multiplying matrices that we have AA and AA, that won't be the same. For left multiplication it acts differently. For right multiplication it acts differently. So the determinants that we derive, they will be different. For one determinant is y square, the other is y. But it is inside GL2R, which is actually unimodular. So that's one thing. And there is something called modular function which actually captures how bad this group, or how far this group is from being unimodular. Alright. So another important thing that I want to discuss other than unimodular groups are amenable groups. So what are so recall that amenable group G is amenable if phi from CB, if there exists a phi from CBJ to C, left harmony actually. No, harmony is for compact groups, it's not for a normalized invariant. Okay. So G is amenable if there exists a normalized invariant mean, right? So what we have shown is that compact groups are amenable. Because we were able to find R measure, since G is compact, we can actually make it normalized, and it actually turned out that it's also right invariant. Fine. What is known? So what is also known, although I will not be discussing, is that abelian groups are also amenable. And the proof of this, actually there's an elegant proof in Rudin functional analysis, chapter 5. So where they use the Rees fixed point theorem to actually come up with a nice proof of this particular fact. Although that's and alright. So that means R, Z are all amenable. So you do actually have a particular linear function like this. Alright. So and I would like to so these are some of the inverted groups, and actually what in the upcoming talks what we do is that we carry out all these the representation theory that we did on finite groups. It's also possible to do them on these compact amenable groups. And so there was a particular conjecture on amenable groups, and it was that so it was von Neumann who actually gave this particular definition. So and he has shown that not every group is amenable. So the free group on two generators is actually not amenable. And he made a conjecture that every non-amenable group is actually contains a free group or two generators, which is known as von Neumann conjecture. But it was shown to be false, and numerous examples were given which were not amenable and didn't have this particular. So, alright, yeah, I mean, this is what I wanted to cover. So, in upcoming talk, yeah, we do whatever representation theory on compact amenable groups. Okay, so are there any questions?
Thank you so much for your time. Thank you so much, Aprameya. And the upcoming talks, the timings will be announced.